Shift F5. All right, so we just finished talking about some examples of covalent bonds and how they make octets for all of the atoms that are involved. We need to talk about the next thing, which is coordinate covalent bonds. And the question is, how are they different? Oops, sorry. Turn my pen on here. How are they different from covalent bonds? So these are coordinate covalent bonds. They're different from covalent bonds. Let's see how. So in carbon monoxide is dangerous. It goes into our blood cells and keeps us from being able to put oxygen into the red blood cells. So it will kill you if you get too much of it. That's part of the reason we have detectors in houses for carbon monoxide. It has a stable configuration, but the oxygen has a stable configuration, but the carbon does not. So if we take our carbon, has 4 electrons, right? Oxygen has 1, 2, 3, 4, 5, 6 electrons in its valence shell. So therefore 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 4 plus 6. Makes sense. So notice, how many electrons does carbon currently believe it has? 6 electrons, because it has these ones that are in the bond and then the other one that's around the side. Yes? Yes? Next statement. How many electrons does oxygen think it has? 1, 2, 3, 4, 5, 6, 7, 8. As an octet, so therefore it's more stable. So that's what it means by stable. Now, if you look down at your electronic structure, you'll see that we have our, once again, 1s electrons, which don't really do anything. We have our valence electrons, 2s and 2p. Oxygen contributes 1, 2, 3, 4, 5, 6 electrons, and carbon contributes 1, 2, 3, 4. Now, these two are paired, those two are paired. And this one, well, we don't have a pair there. It just you have a double pair in the oxygen, but it doesn't fill up the carbons as well because carbon doesn't have those extra electrons to share. So, what? Because it doesn't. Well, because carbon doesn't actually have the other electrons.
But I think, wouldn't carbon be more content in the 4 electrons?
No, it would be more content in 8. Yes, but it would not be more content in either 6 or 4. I don't know that there's really. If there's anything it'd be contented, it'd be 5, but whatever. We don't really, there's no, this is not a situation where half filled is better.
Okay.
Half filled is primarily better in the transition metals.
Okay.
That's the one where it's really important. In this case, really 8 is what we're aiming for every time.
Okay.
All right, so the dilemma is solved if the oxygen donates one of its unshared electron pairs to electron for bonding. So it takes one of these electron pairs, puts it in there. We get this molecule, which could also be drawn as that. It's supposed to be a C, not a G. Okay? Oh, wait. Stop it. So, you can also be drawn that way. Now, so a coordinate covalent bond is a covalent bond in which one atom contributes both bonding electrons. So notice, 2 bonding electrons donated from the oxygen. This is therefore a coordinate covalent bond because one atom is contributing both bonding electrons. In the structural formula, we can show coordinate covalent bonds as arrows that point from the atom donating to the atom receiving. So from the atom donating to the atom receiving. So once again, in a coordinate covalent bond, the shared electron pair comes from one of the bonding atoms, not from half from each. I think this is going to give an example. Yes, example. So a polyatomic ion in like NH4 plus, it's the whole atom, or sorry, the polyatomic ion is tightly bound together, has a positive, what? Oh, it's an example. So a polyatomic ion, we did those already. A tightly bound group of atoms that have a positive or negative charge and behaves as a unit. This is an example of one that has a positive charge. But in general, polyatomic ions can either have positive or negative. All right? Most plants need nitrogen so that they can grow. One of the key elements they need in the soil. So here are some molecules. These are common molecular compounds. Look at the first one, hydrogen peroxide. We have our oxygens in the middle, right? And then we have our hydrogens on the outside. And we have a single bond between the oxygens. We have some extra lone pairs. Oops, covered one over there. And then we have our hydrogens on the ends. This is a colorless liquid when pure. It's used as a rocket fuel. Useful. This is also the thing that you can buy from the store in those brown bottles for an antiseptic. Now, sulfur dioxide is another molecule. Notice your chemical formula shows the number of sulfurs and oxygens, and then we have our actual structure is shown here. This has some of these coordinate covalent bonds in it, okay? Notice, what do you call that bond, the one I just pointed at? It's a double bond, right? The one on the right, this arrow, is a coordinate covalent bond. So it's a single bond, but it means that both of the electrons were donated by the sulfur to make that bond.
So is it kind of like an ionic bond?
Similar. It's like a really polar covalent bond, sort of. But it's specifically that one donates and they are part of a covalent bond. Because covalent versus ionic depends on the types of atoms involved. So if I have covalent is always from one area of the periodic table, you have your two elements from the top right. You could have two non-metals, it's covalent. If you have a non-metal plus a metal, then it is ionic.
Oh, okay.
And so that's the definition we have for covalent and ionic.
Oh, okay.
And the reason for that is that the electronegativities of nonmetals and metals are so different that in ionic case the metal will lose the electron to the nonmetal, whereas in the covalent case they will not. Yes, Haley. So the arrow will point from the one that donates to the one that receives. So does that answer your question? Okay. So it does matter. And you will usually figure out which one donated by looking at the Lewis dot structure, the structure that we draw with the dots. Yes?
Is it like the one that has
It depends on exactly what we have. So let's go back and look at our example here. We'll do some more examples in a little bit, I expect. But we start here. We start with carbon, which had 4. Actually, it looked like it had 6, right? Carbon had the following. And oxygen had that, right? So carbon needed some to get an octet. It currently had 6. It needed 8. So these electrons moved over here because oxygen had 8. It was willing to move one of these over here and become a bond, so it became carbon with that, and then it had 3 bonds, or the other way you could draw that is like this. So the one that donates is going to be the one that has enough. The one that receives is going to be the one that needs more. And so, like if someone has enough money, you don't give them more money. Usually, the person who has money gives it to the person who doesn't have it. So that's usually how you figure out which one it is. We'll do some examples in a bit. All right, so here's sulfur dioxide, sulfur trioxide. It's a similar thing, but it has two coordinate covalent bonds in it. The sulfur gives its electrons to produce the covalent bond between sulfur and oxygen in both cases. Okay, nitric oxide. In this case, we have a double bond in the middle, which is it's not a coordinate covalent bond. It's the electrons are shared equally by both sides, provided by both sides. In nitrogen dioxide, there's one that is they both contribute. The other one is entirely contributed by the nitrogen and then shared between the nitrogen and oxygen. Nitrous oxide, same idea. Triple bond is a bond formed by equal contributions from the nitrogen and the nitrogen, whereas the nitrogen and oxygen is formed by electrons given by the nitrogen to make a bond with the oxygen. So hydrogen cyanide is a similar idea, but in this case, the carbon-hydrogen bond, is that a coordinate covalent bond or a non-coordinate covalent bond? It is coordinate. It is not coordinate, sorry. It is a non-coordinate covalent bond. It's a normal covalent bond because the electrons were contributed by both the hydrogen and the carbon. They were not just from one. Same thing goes for HF and HCl. Right. Any questions about coordinate covalent bonds so far? Mark, what are you doing? On what? Well, what are you using to take your notes? Oh, all right. I was wondering because you kept on looking at your lap, but I wasn't sure what was going on. Okay. All right. So let's move on. Let's talk about how to draw an electron vector structure for a polyatomic ion. H3O plus is a hydronium ion. It's an acidic, what we associate with acidic things. Okay. It contains a coordinate covalent bond, and it forms when a hydrogen ion is attached to an unshared electron pair in a water molecule. So if we take an H plus and we attach it to an unshared electron pair in a water molecule, it's going to kind of attach to one of these and form a bond. Now, we will draw the electron structure. So give it a shot, see what you think it's going to be. We're going to have an oxygen and two hydrogens for water, and then we're going to have it attached to another hydrogen from hydronium. The whole thing is going to end up being positive, by the way. Give it a shot and see what you can come up with, and I'll show you what I have. Question, Caleb? No? Okay. May I suggest looking at these example structures here as a layout? You want? Yeah, you have the slide. So look at slide on page 31. Slide 31 of 50. If you need some added examples that might help you draw these. When you're done, raise your hand so I know you completed it. So we can move on. You're looking it up.
No.
Building in a nap? That's not what I asked you to do.
Well, I'm trying to figure. Well, because I want to figure this out.
Okay, write it down first.
But I did. But
Oh, okay. All right, then that's good. If you already wrote down what you thought the answer was. Okay. The way I would suggest you start this is to draw the Lewis dot structure for the water. Do the water by itself first, and then bring a hydrogen in and see how you would attach that in. There's some suggestions in the paragraph. Hydrogen plus. Makes it easier to messes everything up. That's great. Wow.
It's so much easier. You can put how it's done.
So doesn't that mean that a hydrogen has no?
Correct. Because it had one and now it has none. It lost one.
Wait, what? It lost in a black.
Ow!
Oh, that makes no sense.
Hydrogen had an electron, right? Normally. But it loses the electron and becomes H plus. Let's see what the next part is real quick. Nope. Okay, yeah. Good.
Yay! I think I did it right.
Indeed.
I don't understand how it's possible.
Okay, so if we look at hydrogen on the periodic table, what subatomic particles does hydrogen contain? One proton and one electron normally. How would you make it into H plus? Lose the electron.
But then how does the bond work if there's no electron?
That is the question.
Yeah, but
What she said. All right. So now I'll show you what my answer is in a few moments. They actually have it drawn for you, so I'm not going to try to draw it right now because it's going to get messy. All right. So the H3O plus forms by the addition of a hydrogen ion to a water molecule. Draw the electron dot structure of the water molecule, then add the hydrogen ion. What I suggested. Oxygen must share a pair of electrons with the added ion to form a coordinate covalent bond. So the oxygen has to share some electrons because there aren't any other electrons for the hydrogen to use. So if we look at the answer that they have, you take your H plus, the proton by the way, because we have no electron attached there. We have our water molecule, right? This is my Lewis dot structure for that. I have 8 electrons around the oxygen, and this, so one of these in the bond came from the hydrogens next to it. Now, to get to a hydronium ion, we take these together and we take this hydrogen and we share a pair of electrons with it. A pair of electrons off the oxygen, we share them and we form a coordinate covalent bond. So, if you did the Lewis dot structure, it would look like this. If you drew the coordinate covalent bond in a structural formula, it would look like this. So there's an arrow. Questions? Yes. Yeah, we'll do some more. Oxygen hydronium ion has 8 valence electrons and each hydrogen shares 2 valence electrons. This satisfies the need for both hydrogen and oxygen for valence electrons. Cool. The water molecule is electrically neutral and the hydrogen ion has a positive charge. The combination of these two species must have a charge of +1. So notice, they did a bracket around it and then put a plus up here. That's how you indicate that your ion, the structure that you've drawn, has a positive charge on it. Put a bracket around your structure and then you put the charge up above it. Yeah, Alex?
Are you recording this?
Yes. All right, so if you want, you probably can't hear them, but they're yelling at you, Emily Kenzie. When you watch this, my microphone's kind of unidirectional and localized, so you could if you want.
Maybe none of us are actually on the
Ooh.
Hi. We miss you.
Well, I wonder if I can. There is a way to make my webcam work, but I don't know how to do it, so we'll figure it out later. All right. I hope you heard all of that. Moving on, huh?
You could be like that biomed guy.
Yeah. Bozeman. All right, so let's do another one. Draw the electron dot structure of the polyatomic ion boron tetrafluoride.
Wait, what? Is the whole thing negative or just the fluoride?
The entire thing, the entire polyatomic ion, which is like here. This entire thing was positive. The entire thing is negative in this case. I'm gonna do a bunch of these. See if I can figure out some good examples. 3. You want some light? Mark, you want to get the light? Here's a. Oh dear. Stop! It hurts! Where he should probably die. What? Why is it a minus? Nope, both things minus. So if I said SO4 2 minus, why is it 2 minus? The whole thing. So therefore it's the entire thing.
Negative. Looks like a spaceship from the interweb. Why not? Then how do you get to take one away from the 8? You just can't. You just can't. Where do you add it? You just do. You just do, Adam. F already has 8 around it. No.
With the contraption, right?
Evil. Oh, we have lab today, don't we?
Yeah. We do have lab.
Then why can't you just take away? Just use it, right? That's how you do it.
Ba-dum-ba-dum-ba-dum-ba-dum.
Oh,
Yes. Shall we show you how it's done, gentlemen and ladies?
yes. That's what I meant.
BF4 minus. So here's how we go about doing this one. We do it this. Here's how we do it. With science, right? Moving it. Wow, I heard that. Yes, Mrs. Trott is my computer. She has special powers. That's frightening. Okay. Whoa. Stop it. All right. What is it doing? Oh, I know what I did. Sorry, hold on a second. I need to shut my. All right. As we were. So. Black. Good color. Now, I put my boron down. How many does boron have? 1, 2, 3. How many does fluorine have? So I'm going to put a fluorine over here. And I'm going to share one and draw 6 others. Okay, so boron has shared all of its electrons. So therefore, where does the other electron have to come from? From the interwebs, baby. It comes from the other fluorine. So if I bring my fluorine in, it actually has 7, but if we put the negative in there, we have an extra electron floating around. So I put them like this. Now, these two are a coordinate pair. Oh, I know what I did. Sorry, hold on. Teaching, personal. Teacher, there we go. Interesting thought. So, yeah, it's possible. Yeah, it's possible. So in this case, this is actually, sorry, correction. This is what I want to see from you. It's hard to tell whether it's a coordinate or not because we have an extra, it's a negative charge. So the negative charge could be on any of these, and we don't know which one it came from. So we'll just go with the negative charge here, not call it a coordinate covalent bond. Yes, that's the plan.
Wait, what if you did it with the arrow?
Don't do it with an arrow. Just do the colons.
Wait, do you have any software?
Yes, it's called writing on a piece of paper. There are softwares you can make them on, but this is better.
What about FET?
There is something on FET, but I want to show you how to do this on with your fingers and hands and pen because you're gonna have to do that on a test, which is coming soon. All right, so let's do OH minus. So go for OH minus. I'm going to write some others on here for us to do.
Oh, I know. Oh. Done. Money.
Oh, that's a good one. Let's do yeah.
But I feel like that's not. Well, because remember, yeah, because you're adding an electron. Oh, wow, this changes things.
What? You can do doubles or singles. Just, yeah. All kind of covalent bonds are valid in this case. I'm not sure that there are many double coordinate covalent bonds. That's not very likely. You can, but you get the point wrong. You get the question wrong. Freedom. Oh, freedom. Yeah, right, whatever. All right, so let's do OH minus. How are you guys coming on these? Okay, let's do OH. Write down O and H. So O has 6, right? H has how many? 1. So these two are going to be shared, and we get. Nope. NO2. And in this case, this is OH minus, so we put our other electron here. Yeah. Yes. Correct. Oh, sorry. Let's do SO2. So I'm going to put my sulfur down for this one. What does sulfur have? Sulfur has 6. 1, 2, 3, 4, 5, 6. Right? Add 6. I have 3 oxygens. Really? SO3, 2 minus, 2 plus. SO3, SO4. Sorry. SO4, 2 minus. Just kidding. Oh, actually, that works too. It's sulfite, so. Oh, come on. SO3 is fine. All right. So, let's see. On the second one, I take my sulfurs. Oh, O's. It's supposed to be O's. Oxygens, right? This oxygen I'm going to draw in this manner because it has 6. This one I'm going to draw in the 1, 2, 3, 4, 5, 6. That way. So I'm going to draw this way. Okay. So let's go over the second one here. SO3 2 minus. I draw all my atoms in. Caleb, you with us? Yeah. SO3 2 minus. I draw all my atoms in with their electrons. I'm going to make a bond out of those two. I'm going to make a bond out of these two being shared with that. And I'm going to make a bond out of those two. You could draw that if you wanted. But I want the other electrons. So it's easier to keep track of the electrons if you do dots for everything. Okay. No, I can't. Sulfur has to be in the middle. And so, yes.
Why can't you put these electrons, like put all 6 of oxygens around here? That way sulfur is not going to.
Well, then the electrons need to be donated by the oxygens. And sulfur starts with some electrons, so you can't pull them all off the sulfur.
Okay.
Right. So sulfur started with these number of electrons. This is an SO3 2 minus, right? So we need to put 2 extra electrons in here. They're going to go here and here. And notice what you get. You get something that looks like nope. It was. So that's your answer. With a bracket around that and a 2 minus. Now, Lauren, you got You can do SO4, that's fine too.
Oh, is it the same answer?
Yes, same thing.
But I didn't do coordinate.
That's okay. I'm just showing the coordinate too. So you'll notice another way you could draw this. Attention, everyone. The other way you could draw this is like this. So you could draw it like that as well. You do it that way as well. So either of these answers are correct. All right. NO2, nitrogen with 1, 2, 3, 4, 5. And we have 2 oxygens. Oxygen with, oxygen with 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Yep. So, put these together. What do we get? What is gonna share?
The nitrogen, the oxygen.
Right. So these electrons are going to be shared by both. Okay. And we get oxygen. And then there are 2 electrons here and an oxygen over here. Now, the nitrogen in the middle, how many electrons does it have?
It has 7. 7.
It currently, oh, right, I didn't draw these in.
7.
1, 2, 3, 4, 5, 6, 7. And all of them have 7 right now, right?
No, but you can do something else.
What can you do?
You can do giving electrons or something like that.
Possibly.
Well, do like with those arrows, like you give electrons from oxygen.
We need to find a way so that everything has an octet.
There's double bonds on here?
Double bond could be a good way. Let's try that. So, if I take these electrons and I rotate them around so they're sharing in between here, I get O. Something like this. Nitrogen, hold on, let me make sure that nitrogen's 5, 1, 2, 3, 4, 5. Oxygen is 6 each. Okay, right? So this gives me 8 around this oxygen. Can you see my dots? Kind of small.
8 around the nitrogen.
There are 8 around the nitrogen, and there are 7 around the oxygen. Right, it's a problem, but it's not a problem we can fix right now unless we have an extra electron to put in there. And we don't have an extra electron. So, let's try triple bond, see what we can do. Where do we want to take electrons from to get the triple bond? Yes, however, the problem is that would give us 9 bonds, 9 electrons around the oxygen, which wouldn't work well. So, the way this ends up turning out is this one has 2 forms, as that form and the following form. That's one form. The other form we're going to do in red. That's the other form. How are those two different? Oh, yep, sorry, I missed that. Right, you switch where the double bond is. It's between oxygen 1, this is number 1 and this is number 2. The oxygen, the double bond here is between N and 2. In this case, it's between 1 and N. Yes. Yeah, but then you'd have a single electron sitting in nitrogen. And the world really does not like single electrons floating around. So there are some issues with this one. If we look in the book, that is what happens. I was wrong. So this electron gets pulled to the nitrogen. Right. So it gives one electron left over here. Now, if you look at the textbook, look at the handout. Go back to the page before. You'll find on the page before that we have a chart, I think. Or 2 pages before, there's a chart of molecules. 3 pages before? What page is that? 31. Page 31. Notice, NO has the following structure. Looks like you have the oxygen with its 2 electron pairs, has a double bonded nitrogen with an electron sitting on it, and then it has a single bond to an oxygen, which has electrons around it. So that makes this structure there. Let's see, well, hold on. Let me see if I get this straight here. That's there. 1, 2, that's there, that's there. Yep. Wait. It just leaves it there. Which makes no sense to me because that usually gets radicals like that. They're called radicals when there's one electron by itself. They usually react with stuff all really fast. So I'm not sure what's up with this molecule. I picked a bad example that I can't explain. So yes, Elizabeth? This one? Yeah, that's another problem that I'm not sure how to fix. It could. Oh, yeah. That's what it does. These electrons, because this is actually supposed to be an arrow. Okay? And so these electrons come down and form this bond between the nitrogen and the oxygen. Okay? So that gives us, if these are over here, and those come down, then we get this structure down here at the bottom. Yeah. These coordinate covalent bonds are a little confusing. Because the nitrogen is the one that contributes the electrons to form that bond. We go up here. There are 2 ways you can look at this the first one. What I said is that these 2 electrons would be shared. Oh, that's not high enough. No, it is high enough. The 2 electrons here in this between the nitrogen and the oxygen would be shared. What really happens in this case is that this electron is actually down here at the bottom, and it doesn't make any sense to me. These don't make any sense to me. I don't know why that. Yeah. I will see if I can make better sense of this, and we'll come back to it later. In any case, let's keep on moving with the other stuff, and I'll try to give an explanation for this later once we get farther into it. But we did have some practice working on drawing our Lewis dot structures, which is one of the things we needed to learn. So, can you shut the lights off again? All right. Yes. No? Yes, no. No. All right. So, dissociation. What does dissociation mean? To break them, right. Association is to hold things together. Dissociation is to things to fall apart. We will continue with this tomorrow. Yes? There are some of them that are okay with not being octets. I'm sure there's a reason, but I don't know what it is off the top of my head.
Mr. Trott, we didn't go through 8-2 worksheet.
We'll get there. We'll get to it. We'll get to 8-2 worksheet after we get done with the lecture part. Yes.